Let's solve another thermodynamics problem involving a process that takes place in a rigid tank. A closed rigid tank is filled with water. Initially, the tank holds 9.9 cubic feet of saturated vapor and 0.1 cubic feet of saturated liquid, each at 212 degrees Fahrenheit. The water is heated until the tank contains only saturated vapor. For the water, determine A, the quality at the initial state, B, the temperature at the final state, and C, the heat transfer in BTUs. Kinetic and potential energy effects can be ignored. So let's lay out our five-part solution to the problem stated. We'll start with the schematic. We've got a rigid tank filled with water, and I've drawn the boundary of the system around the water molecules. We're given that at state 1, the volume occupied by saturated vapor is 9.9 cubic feet, and the volume occupied by saturated liquid is 0.1 cubic foot. So obviously the total volume of the tank is 10 cubic feet. It's a saturated mixture at 212 degrees Fahrenheit. After it's heated, it's only saturated vapor, and that's all we know about state 2 at this point, is that it's no longer a mixture, it's saturated vapor. We can visualize this process taking place by drawing a TV diagram. So initially we're at a temperature of 212 degrees, and because it's a saturated mixture, it's underneath a vapor dome. And so we'll visualize that at just some point here. And we know that the heating process takes place at constant volume, and more specifically, constant specific volume, because the tank volume is constant, and being a closed system, the mass in the tank is also constant. So this process will be plotted as a vertical line at constant specific volume until we reach the saturated vapor line, and that's where state 2 is. It's at the same specific volume as state 1, and it's a saturated vapor. And it's at some unknown pressure, P2, and some unknown temperature, T2. And we're going to have to find out what T2 is. To model this problem, we're going to recognize we're dealing with a closed system, that we're going to ignore any changes in kinetic and potential energy as being insignificant, and that it's a constant volume process. And specifically, we want to find the quality at state 1, the temperature at state 2, and the amount of heat transfer it took to cause this problem to take place. So let's begin by finding V1, which is also V2. And to find the heat transfer, we're also going to need U1 and U2. So let's start in the saturation tables for water at 212 degrees Fahrenheit. We see that the saturation pressure is 14.7 psi, and V sub F at state 1 is 0.01675 cubic feet per pound mass. V sub G at state 1 is 26.80 cubic feet per pound mass. Remember that this is a saturated mixture in the tank. There is some saturated liquid and some saturated vapor. So we now have the specific volume for both of those fluids. We also want to find the internal energy. So we're going to get a value for U sub F, which is 180.1 BTUs per pound mass. And let's grab a value for U sub G, again as state 1, which is 1077.6 BTUs per pound mass. Now we need to find the quality, all right? And remember that from a previous lesson, well, we know that the specific volume is just volume over mass. Rearranged, we can say that mass is volume divided by specific volume. And notice that I've used the subscript X here to indicate that we can use many different subscripts in this formula and get correct values. So let's start by calculating the mass of the saturated liquid, M sub F, at state 1. Well, that's just V sub F at state 1 over the specific volume, V sub F, over state 1. Well, the volume at state 1 of the saturated liquid was 0.1 cubic feet. And we looked up in the table and we found that the specific volume of that liquid is 0.01672 cubic feet per pound mass. So the mass of the saturated liquid at state 1 is 5.981 pound mass. Let's do the same for the saturated vapor. We know that the mass of the saturated vapor at state 1 is just the volume of the vapor at state 1 divided by its specific volume. Well, the volume was 9.9 cubic feet, and we found in the table its specific volume was 26.8 cubic feet per pound mass. So that gives us a mass of the saturated vapor at state 1 to be 0.3694 pound mass. So the total mass of water in the tank is just the mass of the saturated liquid plus the mass of the saturated vapor. We add those two together and we get the total mass is 6.351 pound mass. Knowing this, we can calculate the equality at state 1. It's just the mass of the saturated vapor divided by the total mass. Well, at state 1, the mass of the saturated vapor was 0.3694 pound mass, and the total mass is 6.351 pound mass. That gives us a quality of 0.0582. Now, as you'll recall our TV diagram, this may not look quite right because we know that the process from state 1 to state 2 was a vertical line, in other words, a constant specific volume. And in state 2 fell on the saturated vapor line, not the saturated liquid line. And you might think that if you're at such a small quality, if you had a constant specific volume process, that you would end up on the saturated liquid line. But do recall, we've talked about this before, that these TV diagrams are they're more schematic than they are drawings. They're not to scale at all. In fact, the horizontal axis is much more logarithmic than linear, and in fact, it's not even that. So don't let this small number think that you've got the wrong answer just because it doesn't look right on the drawing. Now we can find the specific volume at state 1. It's just V sub F plus the quality times V sub G minus V sub F. We have all these values. We can plug them in here. And we get the specific volume of the mixture at state 1. So that's the total mixture, which is the saturated liquid plus the saturated vapor, all taken together. It's 1.575 cubic feet per pound mass. Now, there's another way we could do this. We could calculate it more directly. We could simply go back to the definition of specific volume. It's the volume divided by the mass. And since we're looking at the mixture, we're looking at the total volume and the total mass. Well, the total volume, we said, was 10 cubic feet. The total mass is 6.351 pound mass. Well, it gives us 1.575 cubic feet per pound mass. It's the same value that we got with the other calculation. And now that we have the quality, we can also calculate the internal energy at state 1. The internal energy at state 1 is just U sub F plus the quality at state 1 times U sub G minus U sub F. And again, we have all these values previously given. And so we get the internal energy at state 1 is 232.33 BTUs per pound mass. So now we wish to find some properties for state 2. And we know that state 2 is defined by two properties. One, it's a saturated vapor. And two, it has a given specific volume of 1.5747, which is what we calculated the specific volume to be. So we are looking at our saturation table for a V sub G value of 1.5747. Well, we can't find it in the table, but we find it somewhere between these values given at 410 degrees and 420 degrees. So we're going to interpolate between these two rows in the table to get a value of temperature and a value for internal energy. So based on the specific volume, which we know, we can calculate an F value for our interpolation formula. And that's just going to be the specific volume, this 1.5747, minus the specific volume at 410 degrees over, or divided by, the specific volume at 420 degrees minus the specific volume at 410 degrees. So we can plug in those values and we get an F value of 0.5749, which means that we're interpolating a value that's just a little bit more than halfway between these two table rows. So let's do the temperature first. Our interpolation formula is that T2 is 410 degrees, which is the first value in the table, plus our value of F times the difference of the values of temperature in the table, 420 minus 410. So we get that T2 is 415.7 degrees Fahrenheit. And we're going to do exactly the same thing for internal energy. We know that U2 is the U value at 410 degrees plus the F value times the value of the U at 420 minus the value of U at 410. Plug in all these table values and we get U is 1118.0 BTUs per pound mass. Let's find the heat transfer by solving an energy balance. So for a closed system where delta KE and delta PE are 0, we can write a closed system energy balance of delta U equal Q minus W. But a rigid tank has no mechanism for doing work. So work is obviously 0. And we can write that Q is equal to delta U, where delta U is a capital U, so that's the units of energy. I can rewrite delta U as the mass times the change in specific internal energy. So Q is equal to the mass, which we saw we calculated a value of 6.351 pound mass, times U2 minus U1, which we previously developed values for. And we see that the heat transfer for this process to take place was 5625 BTUs.